So this is PowerPoint 26. Just to keep you guys in the loop a little bit, this today is what we're going to do. And after that, there's only two more real topics that I want to go over. They're going to be, you know how we did RC circuits? They're going to be LR circuits, which are inductors and resistors, and the LC circuits, which are inductors and capacitors. We'll get to that one. Those are the two last topics. And then after that, it's going to be reviewed. So we're actually very close to the end. The Hall effect. You guys have seen this because it works in almost everything that uses a magnetic strip. So you guys have swiped your card somewhere to get into the building. Do you guys have access to that, or is that just teachers? You guys get to swipe down. So that uses something called a Hall effect. And basically, what you're doing is you're putting a magnet in or around a circuit, and it makes the circuit behave a different way. And that you putting that magnet and creating a magnetic field is what's changing how the circuit behaves. So so I'm going to just very briefly show you how it works. So here, let's say there's a circuit, and it's drawn in black here. So there's a circuit like that, and instead of it being a wire all throughout, this circuit is going to be wire all along this black line here. And then it attaches to a plate, a conductive plate. And then the wire, the other end of the wire, the other end of the circuit is connected and then goes to the other end of the finishes off and does whatever it needs to do. But whatever it is, the current that comes in here needs to pass through this plate. And if there is no magnetic field, right, then the current will just go straight because it's going to be the V is going to be high here and the V is going to be low here. And the electron is going to, or the proton rather, if you're thinking about it with positive charges, whatever it is, the charge is going to want to go from high potential to low potential. Okay, or the electron is going to want to go from low potential to high potential, depending on how you want to look at it. But those electrons, as they're passing this plate, are actually free to move anywhere they want in this plate, right? They're only doing so because that's where the lowest potential is, and charges are going to go towards the low potential. However, if I put a magnetic field across this plate, all right, then there's going to be a force. So if there is a magnetic field in this case, the magnetic field shown is upwards, right? And the current coming in is going to be, I'm just going to draw a dotted line. I'm going to draw the current that way. Those charges are going to feel a force, right? Because it's a current in a magnetic field. And we said that when you put a current in a magnetic field, it feels a force. You guys remember that? Yeah, so you have to use your right-hand rule to figure out what's going to happen with a force. All right, so current is that way. Magnetic field is upwards. And so therefore, there's going to be a force in which direction? Out of the page, or I mean, like towards that blue arrow. Okay, so there's going to be a force here. All right. Oops, that's right. FM. So there's a magnetic force in that direction. Yeah. Why isn't it the same? You're talking about this I current here? I haven't explained that part yet. Okay, I want to get to it in a second. And so, so there's going to be a force in that direction. So what's going to actually happen if I have a magnetic field is that I'm going to send my charge here. My charge is going to enter this plate, and now because there's a force, my current is actually going to do this. All right? And the reason it's going to do that is because there's still a low voltage point where all my charges are going to want to go towards, right? But it's just that they're going to have to take a detour because they're going to feel a force in a certain direction. All right? Now, that's cool and all. What does it matter if it's still going to end up in the same way? But what really matters here is that now what you're doing is you're artificially creating a new voltage differential. Now the voltage on this end versus the voltage on this end are going to be different because now you have a higher concentration of charges on one end of the plate compared to the other. So you're going to have another V high here and another V low here, right? And when you have a difference in potential, then you're creating the potential for another circuit. So now if you were to connect this part of the circuit, or sorry, this part of the plate to another circuit and make it do something, let's say there's a resistor, like that, right? Then now you can get a current going into this second part of the second part of the circuit that is totally and spatially unrelated to that first circuit. The only reason you got that new circuit is because you provided a magnetic field, right? So imagine now that you got these two currents doing whatever. One of them is just doing what it's supposed to do, and the other one has no magnetic field. And all of a sudden, you bring your card magnet, right? And you bring it close to this, and your card magnet is producing a magnetic field, all of a sudden now you're activating, by bringing your magnet close to it, you're activating a new circuit, right? And that new circuit might do a different function, like unlock a door or set off a trip sensor or whatever, right? And that principle is called the Hall effect. Did I explain that okay? Did I answer your question, Shani? Yep. So there's another explanation for another drawing for it. Essentially, is when you have a higher concentration of charge on one end of a plate compared to another, you're creating a voltage differential, and a voltage differential is a EMF. We're going to talk about EMF a lot today. Maybe I should just introduce it now. EMF is electromotive force. Not FDE. An electromotive force, we've been only talking about it so far as a voltage. It's the same thing. Okay? So you're basically, by having this difference in charges, you're creating a voltage difference or an electromotive force, and you can do stuff with that. In this case, what I showed you in my last drawing was another circuit. You're powering another circuit. Okay. So here the current would have come, and then something like this, and then you're creating a voltage difference here. Okay. And you see here that they put the voltmeter in the left and right, and they saw that there is a voltage difference. They call that the Hall voltage. That's VH. I mean, that's pretty much it. I mean, there's not much more to it. It all depends. There's going to be angles and all that depend, but that comes with the whole force thing that I was talking to you guys about before. So I'm not going to explain this part here. We've already talked about it. Nothing. We good with that? Yeah. Why is it useful? So, like I said, you could activate a part of the circuit by bringing a magnet close to it, right? So, if you were to, as a user, bring or turn on or somehow provide a magnetic field, you can activate that second part of the circuit. So remember, I said, let's say that this end of the plate was connected to another resistor, and this resistor does whatever you think it needs to be important, right? You could activate this circuit by bringing a magnet close to it, by providing a magnetic field here. All right, so that's that. That's the Hall effect. And now, please bring PowerPoint number 27, which is induction. They're repeating the same stuff. Wrong PowerPoint. All right. You guys remember I had this little drawing of the mass confusion thing when we did Gauss's law? It's back. Actually, I didn't come up with these slides. These are Mr. Wakarski's slides. So he actually put them. So he agrees that these are not easy topics to grasp. I have this as part one and part two, but part two is really just a revision of part one. So all the theory actually comes in part one. So you're going to learn two laws today, Faraday's law and Lenz's law, right? They're kind of showing the same thing, but two aspects of the same thing. They're both talking about induction. And then we're going to try to understand a little bit how this whole induction thing works. Remember how I said, so we talked a lot about current and magnetic field, but it's just so confusing. So let's recap what we've done already to see how this, what we're going to look at today is going to be different. So we saw that a current can produce a magnetic field, right? You guys remember that? That was Ampere's law, right? So a current can produce a magnetic field. We also saw that a current in a magnetic field will feel a force. You guys remember that? Okay. So now what we're doing is talking about how a magnetic field can induce a current, right? And that's why it's called induction. So a magnetic field is going to cause a current to occur. And there's concepts of flux that we need to understand. There's concepts of the changing of flux. So we need to talk about the rate of change. When we're talking about rate of change, we're talking about differentiation. Okay? We good so far? All right, I don't know why my screen is so dark. I can hardly see it. Give me just one moment. I'm going to try to make it brighter. Oh, there you go. Yeah, sure. Good. Okay. This one here? Or this one? Yeah. Yeah. It always works better when I have diagram. This is really for you guys to study with later on. The important thing of today is going to be something called Faraday's law. And Faraday's law is that when you move a magnet near a conductor, you'll induce a current in the conductor. So let's say you have a wire and you have a magnet and you move the magnet in and out of that in the field of that wire or that conductor, then you're going to have a current in that conductor. Okay? And it really hasn't to do with the strength of the magnetic field. It 100% has to do with the change of strength of the magnetic field. All right, so that means that if there's a high rate of change, then you're going to induce a high. Now we're going to talk about EMF. You're going to induce a high EMF. All right, so you're going to have a stronger current. Whereas if you were to just slowly bring a magnet close to a conductor, it's actually not going to do anything, or it's going to do very little that you're not going to notice it. All right, even if it's like a super strong magnet, it really has to do with the change in magnetic field. So that's it. So the change of a magnetic field close to a conductor creates an electromotive force. It's basically the most important part of this. And again, it's the rate of change of the magnetic field that is proportional to the EMF. Okay. So let's see how that works. We need to figure out what this thing called flux is. And we learned about electric flux when we talked about Gauss's law. But now we're talking about magnetic flux. Is red an okay color? No, right? Better? Yeah. Can you guys see, or is it too bright in here? Fine. You want me to turn off the lights? I'm afraid of you guys falling asleep. So, okay, so flux here is the same symbol as what we saw before, and it's the same concept. It's the dot product of the magnetic field and the area. That's the dot product. And so basically, if you guys remember, when we were talking about flux and Gauss's law, was that there was the amount of the electric field lines that would enter this surface area, and that surface area had to be measurable to some certain extent, and you would get that that the flux is basically how much electric field lines are entering per unit area or for the unit area. You remember that it was the surface integral of B dA. You guys remember that a little bit? And that if it was a uniform magnetic field or uniform electric field, you can take the magnetic or the electric field out of the integral, and so you would have B integral of dA. And then the integral of dA is just A, it's just the area. Okay? So I can do this if uniform magnetic field. All right, so the practice. All right, I'm going to try. Better? Yeah, it looks like I'm crossing it out, but it's just my pen that glitches once in a while. Yeah. Yeah. The unit Webers are for magnetic flux. Right? And do you guys remember how it was? Like let's say the screen was my area in which the magnetic fields are going. What orientation does this need to be compared to the magnetic field lines in order for me to maximize my flux? It had to be 90 degrees or perpendicular, exactly. And if it was on an angle, then it would be less, right? And if it was parallel to it, then what would my flux be? 0. Okay, very good. There is a way to calculate mathematically the flux if I wanted to measure it at different angles. So my flux at different angles would be B A sine theta. Was it sine theta or cosine theta? I can't remember. It was cosine theta? I'll take your word for it. The dot product is cosine theta, right? Yeah. Okay. So this would be at any angle. That's any angle between B and A. Yeah, exactly. This seems pretty familiar to you guys. It's also a little bit of a review. No PTSD or anything like that. And so look at the parallel. It's haha, no pun intended. But look how similar they are. It's the number of magnetic field lines passing through perpendicularly into an area. One of them is for magnetic field, the other one's for electric field. So one's going to be called magnetic flux, the other one's going to be called electric. Really just very, very similar. Just take notes of the units because they're quite different. And again, this Tesla meter squared is referred to as Webers. So Faraday's law is that we need to, now that we understand the idea of magnetic flux, Faraday's law states that in order for you to understand how much electromotive force is produced, you need to measure the change in flux, right? So the EMF produced, so this is the EMF produced, is going to be proportional to the change or the delta phi or the delta flux over time, right? And that's not always going to be obvious. It's not always just going to be delta. So we rewrite it as the derivative as a function of time of flux, all right? You hear? Well, I guess you can say that they're equal, but this is going to be for big changes and these are going to be for small changes, for small deltas. E, yeah, E is electromotive force, EMF. We're going to need to know a little bit about direction, right? That's going to be Lenz's law, and we're not there yet. So this is just Faraday's law. Faraday's law says that when there's a change in magnetic flux, there's going to be an induced EMF, which is going to induce a current. All right. Yeah. Faraday's law. Playing games there? Oh yeah. We're gonna watch one of these videos from this guy. He's actually really good. Does anyone follow his YouTube channel? It's Veriticio. Yeah, it's really, really good. All his videos are interesting. What was I saying? Yeah, so Faraday's law is just that there is an EMF induced. Lenz's law is going to tell us about the direction. We haven't talked about that yet. All right, so let's apply that somehow. So here what I have is a current, a circuit, right? Or not even a circuit. Let's just call it a loop for now. This loop, I want you to imagine this here, this bar here, is a sliding bar that can move up and down this part of the current. Right? This part, not the current, but this part of the conductor. Everything's made of conducting material. All right. So when I have this close here, what can you tell me about my area? Small. And then as I move this, my area is getting bigger. Okay. As I make this smaller, how many field lines are going into my closed part of my loop? Less or more? Less or more? I heard two answers. Less? How many? Just think of this magnetic field is not changing. All right. So how many arrows are going through my area if this thing is smaller? Less arrows are going in, so my flux is going to be less. Okay. So remember that my flux is going to be my magnetic field multiplied by my area. If my area is small, my magnetic field is constant, then I'm reducing my flux. All right, now if I gradually move this at some constant velocity, what's happening to my flux? It's increasing. Okay, so that as I'm increasing this device, or however you want to call it, think of it as like a trombone almost. If I'm increasing this, I'm increasing the area, and what's happening is I'm increasing the flux. And if I'm increasing the flux, I'm inducing an electromotive force. So therefore, as I'm opening this up, there's going to be a current that's going to flow through this loop that I've created with this conductor and this wire here. Right? You guys understand what I'm trying to say? Right? So again, I'm going to repeat that. As I open this up, I'm allowing more and more magnetic field lines to enter my closed loop. And as more and more magnetic field lines enter my closed loop, I'm having a greater change in magnetic flux. And a greater change in magnetic flux means that I'm inducing an electromotive force. All right? And there's the velocity of how fast and slow I open this. Does it matter? Yes? No? Think about it. So if I open this really fast, is it going to be a really big change of flux? Or if I open it really slow, is it going to be the, what do you guys think? Johnny? What equation are you talking about? Faraday's law? Okay, so Shani says that if I open this really fast, then I'm reducing the amount of time it takes, therefore my change in flux is greater. Do you guys agree with that? Yeah, it's a pretty sound argument. So yes, the velocity of this does matter, right? So I change this with a velocity v or a velocity really big V, it's gonna induce a bigger EMF if I go with at a very high velocity. So we can derive some kind of equation from this. It's the equation is at the bottom, but I like to work at it for you guys. So we said that the flux is equal to the magnetic field B dot product A. And, oh, it's in red. Let me just change it to yellow. we say that the flux is equal to the B dot product A, and that the EMF produced is equal to the change in magnetic flux over the change of time, right? So that means the EMF is equal to the change over time of B dot product A. Magnetic field is not changing because in this case I told you that it remains constant, right? So I can take that in front of the derivative. And so it's going to be as a change of area, and my change of area is not changing very drastically in all directions. This part of my square area is remaining constant, so I'm going to call that the length, right? So I'm going to break this up into length times distance, and this is going to be, let's change it to red. This here I'm going to call S. This here I'm going to call L. So my area is going to be L times S, right? L is not changing. So I can take that in front of my derivative. So my EMF is going to be equal to E times L times ds dt. And ds dt, or the derivative of distance as a function of time, is what? The rate of change of distance is, think back to last year, think hard, yeah, velocity, right? So the EMF is equal to B times L times V. Yeah, correct. So this would be correct if we're talking about constant velocity. Yeah. That's Lenz's law, not there yet. Yeah. So far, so good? So let's try doing a problem. Forget about A, because we don't know the direction. Actually, we can't do this yet, because we don't know Lenz's law. We'll come back to this. But we can solve this one, though. So there's a triangle, loop and a wire, da, 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 da. If the field strength changes from 0.3 to 0.10 in 50 milliseconds, what is the induced EMF in the loop? So we just have to apply what we just learned. So we need to know that EMF is equal to the change in flux over the change of time. That we know that the change of, in this case, is the shape changing or is the magnetic field changing? So it's the magnetic field. So it's going to be, and for instead of d phi, it's going to be A d d over dt. So the area is constant, so I can take that out of the derivative, and it's my magnetic field now that's changing. So my EMF is going to be 0.2 meters times 0.2 meters over 2. That's the area of a triangle. Base times height divided by 2. multiplied by the change of magnetic field, and the change of magnetic field is how many? Is it, you guys can tell me this, right? It's going to be negative. It's going to be negative 0.20. It's negative because it's decreasing. And my change in time is 0.05. Yeah. Well, it's just going to determine the direction of the current arrow. It's just not going to matter. Yeah. You can take the absolute value if you want. What'd you guys get? 8? 8? A? Oh, A. I said 8. It's not actually 8. It's 0.08. Cool. All right. Remember to convert everything into meters. Keep everything in SI units. Meters, seconds, etc. Okay. We're gonna have to apply. This one is not intuitive if you don't apply the law. Okay, so these are 4 different situations. It's asking you to rank them in order of flux. All right. So now we're not looking at the change of flux. We're just looking at flux, or raw amounts of flux. So we need to figure out 2 things for flux. Flux is equal to the dot product of B and A. They're all perpendicular here, so I don't need to worry about angles. What could you tell me about the flux about these 4 things? So think about it. Look at the number of arrows, the value that they give you, the area of the piece, and make a conclusion based on that. I'm going to give each one of these guys a letter, and then we're going to rank them by letter. So who has the lowest magnetic field, and then magnetic flux, and who's got the highest one? Yeah. 2. Okay, so it's going to be the area, which is 1 times 1, and the magnetic field, which is 2. So we're going to call this magnetic flux of 2 some kind of units. All right, and C, you said the same thing. A is going to be 4. Yeah. So you have to consider that only half of the area is being used, right? But that doesn't mean that those areas don't exist. So the question is asking you to flux through the whole loop. So it's going to be, I don't know what you mean by 2. Explain. Yeah, absolutely. It's not that they're moving up, it's that you got to take an average of the 2 sections, and then it's going to be 1 exactly. So it's going to be an area of 2. No, not 1. Sorry, it's going to be an area of 2 with a magnetic field of 2, right? So the magnetic flux is going to be 4, right? Yeah, because the magnetic field here is stronger. The magnetic flux will be 4 units. Right. It's because you're right. Because this is the area of the whole thing, and this is the magnetic field, the magnetic flux of just a half. So you can take an average of, yeah, you're right. You're going to take an average of 1. So it's going to be a magnetic flux of 2 units. So B, C, and D are equal, and A is the highest. Yeah. So far, so good? Okay, it's going to get a bit more complicated. So a magnetic field in a circular loop of radius of 1.0 centimeters is decreasing. The function of the decreasing magnetic field is shown here. It's this equation. And so it's asking you what is going to be the current if there is a resistance of 0.1 ohm in the wire. All right, so now it's not even asking about EMF, it's asking us about current. But EMF, remember I said it's the same thing as voltage? Okay, so we need to know that right now because we're going to use Ohm's law. And so therefore voltage over resistance is going to give us current, all right? And the voltage is that EMF that we're trying to calculate. All right, so let's try to calculate that EMF. We know that EMF is equal to the change of flux as a function of time. So when we're talking about flux, is the magnetic field changing? Yeah. Is the area changing? No. So we can take at least the area part out of this derivative. So EMF is going to be equal to A and the derivative of B as a function of time. And it's going to be the derivative of B at time is equal to 6 seconds. So that means we need to know how to differentiate this equation. You guys remember how to do derivatives? Which rule would you use for this one? Yeah, I guess this one is an obvious one. If you were to do this the long way, this would be, you could use substitution to solve this problem. All right, you can also use the chain rule also to solve this. Okay, if you don't remember the identity. So absolutely, the derivative of this, so if I were to take b prime of t, it would be equal to 20 or negative 20 e to the negative. Okay? Yeah. Correct, but now it's not e to the x, it's e to the 2x. So it's a function and another function. So there's a rule on that. I mean, we can, if you want, we can do a substitution. You sure? I want you to be convinced. So this is the derivative of that. So now I can punch in what's going to be the change in magnetic field at 6 seconds. So I'm going to put that 6, so minus 20 e to the minus 2 times 6 seconds. That I won't be able to do in my head, and maybe some of you could help me out here. Because this here is this is what we're gonna put here. The change in magnetic field at time is equal to 6 seconds. Someone have an answer for me? Just for the change, I'm not asking for anything else here. Minus 1.23. Can you give me some units? So think about it. The change in magnetic field is a function of time, so it would be Anyone? Yeah, absolutely. Teslas per second. And just while we're at it, let's figure out our area. It's a circle, and it has a radius of 1 centimeter. So it's going to be pi r squared, pi times 0.01 squared. Give us a really small area. What'd you get at, Michelle? Times 10 to the negative 4. Oh, that's actually possible. Because it's to the power of negative 12, right? That's going to give us a pretty small number. Okay. All right? And just again for the area now. Yep. Units? Yeah. Very good. And so now we can figure out what our EMF is. It's going to be 3.1 times 10 to the negative 4 meters squared multiplied by, well, I'm going to drop the negative, 1.23 times 10 to the negative 4 Teslas per second. That's going to give me an EMF of negative 7 units. I'm not solving for current yet. It's the EMF. So it's not even 3.86. Okay. So I need an answer for the EMF when I multiplied my area and my magnetic field. What did you guys get? What do you think the units are? Volts. Yeah, absolutely. EMF is the same thing as voltage. So that's your induced voltage, all right? So you've produced a voltage differential of this inside this circle, and that is going to be used to mobilize charges in this current that has a resistance of 0.1 ohms. So you can figure out using Ohm's law. So your new voltage, 3.86 times 10 to the minus 8 volts divided by 0.10 ohms, ugliest ohms ever written, ohms. And that's going to be equal to 3.86 times 10 to the minus 7 amps. That's my answer. A bit messy, I'm sorry, I didn't give myself too much room, but I hope you were able to follow. Does that seem okay? Other than the derivatives part, it's pretty straightforward, right? Nick, did you got one? Okay, good. Okay, not switching slides for some reason. Okay, so now for the direction. The direction is going to require some imagination. Should we watch the videos or do the explanation? Let's watch the videos. Break it up a little bit. So I have 4 videos. Some of them are shorter than others, but they're all pretty interesting. Hopefully you can see them. Okay. Sorry, just 1 second. I'm trying to maximize it. There we go. So there's 2 tubes, one of aluminum, one of glass, and he's gonna drop 2 magnets in each of them. Okay. Hello. Oh, this thing is so buggy.
Hello, Jesse Good.
Haha. It's here. Put it here.
Magnetic braking is a type of braking which doesn't rely on mechanical pressure, as is common in most braking systems. We'll demonstrate this type of braking using a magnet and a copper tube. Unlike iron, copper is not a magnetic material, so the magnet won't physically stick to it. Therefore, magnetic attraction cannot be the reason for any slowing in the fall of the magnet. A slit has been cut in the front of the copper tube so you can see the magnet as it drops. As you can see, the magnet falls much slower than you might expect. We can drop a non-magnetic metal through the tube and see how quickly it falls. It falls much faster. Therefore, magnetism must have a role to play in this process, even if the magnet is not being physically attracted to the copper tube. If we look down on the copper tube as the magnet falls through it, you can see that the magnet never touches the sides of the tube. Therefore, friction cannot have a role in the magnet's deceleration. Using the following cartoons, we can explain the processes that are actually happening. Again, we see the magnet dropping through the tube. The red lines are added to represent the magnetic field produced by the magnet. As the magnet falls, the magnetic field in the copper tube changes. This variation in the magnetic field induces an electric current, as predicted by Faraday's law. Faraday's law states that any change in the magnetic environment of the copper tube will cause a voltage to be induced in the tubing. This induced voltage creates electric currents in the copper called eddy currents. They're called eddy currents due to the circular motion they undergo. All electrical currents produce their own magnetic fields, which are illustrated in this diagram by green lines. Another law predicts the direction these induced electric currents and their magnetic fields will flow. This is called Lenz's law. Lenz's law states that when an electromagnetic field is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced electromagnetic field is such that it produces a current whose magnetic field opposes the change which produces it. Essentially, this means that the magnetic field created by the eddy currents oppose the magnetic field created by the falling magnet. It is the opposition of these two magnetic fields working against each other which slows the fall of the magnet. This video from the MIT Physics Lecture Demonstration Group demonstrates magnetic braking using the copper pendulum. The pendulum swings freely when the magnets are not switched on. Once the magnets are on, the pendulum experiences a changing magnetic field as it swings. This changing magnetic field induces a voltage in the pendulum, which creates eddy currents. The magnetic fields created by these eddy currents slow the pendulum to a stop. This perforated pendulum contains many gaps, and these gaps are occupied by air, which has a very high resistance to electrical currents. Weaker eddy currents means a weaker opposing magnetic field. This results in less magnetic braking or damping, and the perforated pendulum comes to a stop much more slowly than its solid equivalent.
Yeah. No, electromotive force. There is something called an electromagnetic field because by turning on the electromagnet, they're producing a magnetic field, so they call that an electromagnetic field. But they refer to it as EMF with that acronym. That's wrong. EMF is electromotive force, and it's voltage. Very roughly speaking, and it'll become a bit more clear later on. This is just a cool demo. It's kind of trippy, actually. Why isn't it showing? Hold on. I'm trying to let it load a little bit because I think it's like super high resolution. Let me try to decrease the resolution. This is impressive, right? Just because copper is not a magnetic metal. So it actually doesn't feel a magnetic force. So because of the change in magnetic field, it's feeling that change. Again, this is impressive because copper is not a magnetic metal. Kind of trippy, eh? And one last video. This is a Veritasium video. Yeah. We're going to figure out what Lenz's law. All right. And it's going to somewhat explain in this video, and then we'll explain it together in detail after this video.
I have a pipe. Yeah. Do you want to hold it? Do you know what it's made of?
Metal? Is it brass? Copper.
Is copper magnetic?
No.
Uh-oh.
I'm gonna go no, I didn't think it was.
I'm gonna go yes.
Yeah.
Well, why don't we check? This is a magnet, and I'd like you to use it to test whether the copper is magnetic.
No.
I want you to be 100% sure here. What do you think?
No.
It's not magnetic.
I said so.
Okay. Is there anything in there?
No.
What do you see in there?
That's nothing.
So why don't we drop something through it, just make sure it's empty, right? Okay, this is not a magnet, so this isn't a magnet, but let's see what happens when we drop it through. That was a dull experiment, wasn't it?
Yeah.
Okay, so what's going to happen if we drop this magnet down the pipe? It's going to pull through. Let's do it. 3, 2, 1.
That was weird.
It's well cool.
Took longer.
What's slowing the magnet down?
It's got to be magnetic poles or something. I don't know, north, south.
Something to do with the polarity of the north and the south poles.
But it doesn't stick.
But then it's not magnetic, so it shouldn't do anything.
Right, you guys saw that. Like,
That is slightly magnetic on the inside somehow.
It's going to be magnetic inside, isn't it, or something. Does it like...
Kind of tilts. I think it's the powers of the universe.
I don't know why it's doing it.
well, this is what's exciting, is only a few blocks from here was the lab of a guy called Faraday.
In October 1831, he built the world's first electric generator here, a magnet which you push and pull in out of a coil to generate electric current.
So that's the actual...
Yeah, the world's first electric generator.
there's a permanent magnet in there?
That's a permanent magnet, yeah.
It was Faraday who realized that it's a changing magnetic field that actually can generate electric current. So as the magnet is falling through the pipe, it's creating a changing magnetic field that generates little electric currents, so-called eddy currents in the pipe, and they create an opposing magnetic force on the magnet, slowing it down. So it actually turns the pipe into an electromagnet,
I see.
which pushes the magnet up. And this is what's known as electromagnetic induction. So it causes my LED to light up there. But it's important that you move the magnet quickly, because if you move it too slowly, the magnetic field is not changing fast enough to generate enough voltage to light this LED. This is actually the way all electricity is generated.
Is it?
Yeah, you move a magnet near a conductor and it creates electric current. But where is this electrical energy coming from? You can't get energy for nothing. Well, Faraday realized that there must be a force pushing back on the magnet. It's the same force that slows this magnet down as it falls through the pipe. So there's actually energy being converted from gravitational potential energy into electrical energy and eventually to heat. So this pipe is warming up by taking some of the energy out of the falling magnet. Is that any good or what?
Oh, it's very good.
This way. And these currents coming around this way will induce...
Just so you guys know, this guy's channel is Veritasium. He does a lot of really cool science stuff. I recommend you guys watch his videos. Okay, so let's go back to this and explain exactly what's happening. It's a pretty cool demonstration to see something falling with no kind of parachute, no force kind of, well, I mean, there is got to be a force. And we just don't know what that force is, but it all makes sense in a second. And for that, to understand that, we need to understand Lenz's law. And Lenz's law basically is a law of inertia, right? It's the application of the law of inertia in electromagnetics and this whole field. And basically, inertia is that nature or science is extremely lazy and really does not like change, okay? And what it does is, if there is a change, nature is going to do its best to oppose that change. All right, so that's the principle that we're going to go on. All right, so whatever the change is, we're going to try to oppose that change, and that's how we're going to figure out the direction of the current. So here I have a loop, and I have a magnet, and as this magnet, in this case, it says it's moving downwards. As this magnet approaches the loop, there's going to be a change in magnetic field. Okay. And a change in magnetic field is going to induce a current in this loop. So there's going to be a current in this loop, and we're going to figure out which direction this current is. So let's say we broke this down into two separate drawings. Let's break this down into two different drawings. We have situation initiale. That's the south end of the magnet, all right? I drew only 4 field lines coming into it, all right? So remember that magnetic field lines enter the south pole of the magnet, all right? There's 4 of them entering this magnet. And how many of them are passing through the loop? How many? According to my drawing? 2, exactly. And as this gets closer, so this is the second situation finale, all right? Since it's closer, how many magnetic field lines are now into the loop? How much? 4. Okay, so the magnetic flux increased, right? The area didn't change. The magnetic field increased, right? Increase in which direction? In the up direction or in the down direction? In the up direction, all right? So it increased in the up direction. The magnetic field became more up. And as you know, nature hates that change just happened. So it's going to do its best to increase it in the down direction. So how is it going to do that? It's going to induce a magnetic field, right? So, and I'm going to remove that. I'm just not going to draw that magnet. It's going to induce a magnetic field called B induced in the downward direction to oppose it, right? And if it wants to induce a magnetic field in the downward direction, which direction does the current need to be going? You have to use your right hand. And if I were to look at this from the top, it would be which direction? So use your thumb, your hands, try to figure it out. So I'm looking at this from the top, let's say. It's not a force that it's inducing, it's a magnetic field that it's inducing. So remember, a current will induce a magnetic field. Correct. So remember yesterday, not yesterday, but last class, what we learned was, it was a while ago now because we had our test last class. You have to remember that let's say you have a current in a certain direction, right? Let's say I have a current in a certain direction, like this. It's going to produce a magnetic field using the right-hand rule, right? So the thumb in the direction of the current and your fingers are going to wrap around in the direction of the magnetic field. And for a loop, remember we had a drawing of a loop like this, and we tried to say that it resembled kind of like a bar magnet. So all of the magnetic field lines are going like that. And if all the magnetic field lines are going like that, then that means that there's a current in this direction. You guys remember that? So if I were to apply that logic to my golden loop here, which direction is my current going to be going in? Which direction is that? If I'm looking at it from the top, is it clockwise or counterclockwise? Clockwise. It's going to be going in that direction if I want to induce a magnetic field downward. All right, so put your thumb down, and you can see that your fingers are going to wrap clockwise around. So what I've done by moving my magnet downwards is I've pissed off Lenz's law or nature, and I want to oppose the change, right? So I'm going to induce a magnetic field. And how do I induce a magnetic field? Is I make a current in a specific direction. Yeah. Say that again. Yeah. Yeah. There is. I just separated my drawing, so it's not necessary. You can say this and this are the same drawing, same time. Essentially, it's as you're. Okay, let's try it again. Different example. All right, you'll get a hang of it. I have a magnet. This time I'm moving it upwards. Okay, so let's draw our situation initiale. I'm going to draw it closer now. Let's draw it upwards, and therefore there's going to be all four magnetic field lines that are going through my loop. All right, my magnet is moving upwards at the velocity v, let's say. All right, and that's your initial situation. And then after that, situation finale, you have this situation where there are less magnetic field lines in my loop. So did my magnetic field increase or decrease? It decreased. It decreased in the up direction or in the down direction? In the up direction. So if it wants to oppose the decrease in the up direction, you need to counterbalance that by inducing a magnetic field in which direction? Up or down? Up, exactly. You want to compensate for that decrease in magnetic field. So this loop is going to get a current induced into it, and therefore is going to have an induced magnetic field in the upward direction. If you want an induced magnetic field in the upward direction, which direction does the current need to be going? Now you need to use your right hand. Counterclockwise, exactly. This is counterclockwise. Yeah. Counterclockwise. So the answer here would be like this. Take some imagination here. So we're going to practice this a lot right now. You guys do this one on your own. The same thing. Now I'm talking about the north end of the magnet, and it's moving downward. Do you think the induced magnetic field is downwards or upwards? Upwards, very good. Your B induced is upwards. If my B induced is upwards, which direction is my current going to be going in? Counterclockwise. So in this situation, we'll forget about the first drawing here because it's kind of confusing. It's kind of backwards the way they drew it. I have a magnet entering a coil, right? And you want to figure out in which direction the current is going to be induced. Draw your magnetic field lines. That always is what I always do to make this easier. The magnet's getting closer and entering the solenoid. If the magnet's getting closer and entering the solenoid, then what's happening to the, is the magnetic field inside going to be increasing or decreasing? Increasing. Increasing to the left or increasing to the right? To the left. So your magnetic field that's going to be induced is going to oppose that. So it's going to be towards. What's that? Oh, no. Anyways, to the left because your magnetic field lines are pointing towards the left, right? So it's increasing towards the left. Okay. So it's increasing towards the left. So your induced magnetic field needs to be towards the right. If the magnetic field needs to be towards the right, which direction does your current need to be going? There's your B induced. Which direction does your current need to be going to produce a magnetic field towards the right? So now you have to use your right hand rule, where it's going to be, put your thumb towards the right. Your fingers in front of the solenoid are going to be pointing in which direction? Down or up? Down, exactly. So it's going to be like this. Yeah. This is how it produces the current, right? It's the fact that the magnetic field the rate of magnetic field lines is changing, that it's going to try to get it to get opposed. And how it opposes it is by creating a current. And that new current that you just produce is going to produce a magnetic field to oppose it. It's kind of like a byproduct of the induced magnetic field. So in this case, the current is entering the negative end of the ammeter. And so if you had a needle here, it would point towards the negative. This concept here of a magnet inside a coil, inside a solenoid, we call this an inductor. And we use them in circuits a lot. Have you ever, anyone here at home have LED lights? Yeah, like all your light bulbs. I mean, I hope I made a good enough case for it for you guys, but I do implore you guys to change everything to LED. When you turn on or off an LED light, you notice that they don't turn off and on, like switch on, switch off. They kind of like dim on and dim off automatically. And that's because there is an inducer in them. And what that does is it allows the current to gradually increase and to gradually decrease. We'll learn that when we do LR circuits. And that's what makes it so that it glows on its way up and it diminishes on its way down. It's not just an off and on switch. This is good because drastic voltage drops could be damaging to your devices. And when you turn them off, you don't want there to be a sudden drop of voltage. So what you'll do is you'll put an inducer in there so you can gradually drop it. You can control the time constant, and it's kind of like RC circuits. You can control the time constant of how gradual it increases and decreases with this LR constant. Okay, we're good. Let's try to do this one. This one's a bit trickier. So the magnet's not moving. The ring is being moved from left to right and is asking you to graph its current. And it's telling you that the clockwise current is negative. So again, what I like to do is draw it at different time intervals. So as the ring approaches the magnet, is the magnetic flux increasing or decreasing? As it goes from point A to point B, is the magnetic flux increasing or decreasing? It's increasing, all right? If it's increasing, and it's increasing in which direction? Up, that means you're going to have an induced current down, right? So you're going to have a B induced downwards. And if you have a B induced downwards, which direction is going to be current? Clockwise. So if we were to graph it, it's either going to be B or D, all right? So A and C are now totally out of the question, right? Because a clockwise current is negative according to the problem here. Okay? All right, so we know that it's starting off as clockwise and it's ending up as what? So now as it gets further and further away, is it going to be, is the magnetic flux going to increase or decrease? Decrease in the which direction? In the what direction? It's going to decrease in the up direction. So you're going to have an induced magnetic field in which direction? You want there to continue being up magnetic fields, but it's not because it's decreasing. So you're going to try and compensate by having the magnetic field in which direction? Up, exactly. So your B induced here is going to be upward. And if it's upwards direction, your current is going to be in clockwise or counterclockwise? Counterclockwise. So it's going to be positive. So there's counterclockwise. So it ends up, starts off as negative, and it becomes positive as time goes on. Okay. So the answer would be D. What would the graph look like if I increase the velocity of my loop? Say that again? So you think it's going to be like, if I went faster, you think it's going to be like this? With the same timing? Okay, compressed. What, steeper or, sorry, less steep you said, eh? Okay, so is the amplitude going to be greater than or equal or less than this one? Equal? Okay, so Mark says this. Anyone agree or disagree? I disagree. Oh, sorry, I shouldn't switch. I should be the same direction. But that's not why I disagree. It is at a higher frequency. That's why it's compressed, right? Yeah. Why? Yeah, exactly. So the amplitude should be higher and the frequency is going to be less. Any questions on this? I have another example to practice this yet again, but I think you guys are getting quite good at it. I'm not going to do it. Again, same examples, and this. Okay, now that induced current is called the induced current. When we're talking about in a loop, we call this an induced current, right? I induced. However, if it was through a copper rod, like we saw in those videos, those currents are happening in the walls of the copper tube, and it's not in the circular part of the wall; it's actually in the wall, and that's what's called eddy current. It's just the name of the guy who described this phenomenon. It's still the same idea. They're called induced currents, but the induced currents being in a wall of the pipe, those are just called eddy. Right? So I want to explain that further. I want to show you just one last video. I've kind of spent a lot of time on this. I promise that'll be the last thing. I feel this guy's got a really good explanation of what I want to talk about. It's 8 minutes. Do you want to watch the whole thing or just part of it? Whole thing or just part of it? Part? All right. Ah, crap.
Lines, you can see the magnetic field lines are changing, and as they change, we're getting change in magnetic flux, and so we're getting current inside the wire. Now another way to look at this would be through a generator. And so in this setup what I have is a magnet down here on a wheel so that I can spin that magnet. I have my wire again, and I'm trying to induce current inside that wire, and then I'm going to measure the amount that I'm going to change. And so watch what happens now when I start to turn on the water inside that faucet. It's changing the position of the magnet. As it changes the position of the magnet, it changes the magnetic field. You can see the magnetic field lines are changing. And so I'm starting to get a little bit of current. What happens if I increase the speed of that water? I'm getting more current. We could even have a light bulb connected to it. And so now I'm starting to get usable energy. Watch what happens as I increase the number of wires. I even have more energy coming out. And now if I increase the water again, I even have more energy being produced. And so we're taking that energy of the flow of the water and actually making electromagnetic energy out of it. And so this is how the generators in a dam would work. We have the water flowing down through the dam, it's spinning these magnets, and it's creating that electricity. And so did you learn to construct an explanation?
You understand what he said? Yeah, it's basically how all things are made. And I just want to add something to it. Did you notice that the current was moving back and forth? Right? That is an AC current. Okay? That's how we have AC current coming out of our plugs, is because the generators that are working are spinning in a circle, and so they're providing current in both directions. And rather than converting it upstream and converting it where the factories are and giving us direct current, what they're doing is they're giving us AC current, so none of the current is being wasted. And it's really a direct line from the hydroelectric dams to us. It's very, very, very quite impressive that they're able to do that. And we can convert it if we want. We can have rectifiers and all sorts of things, or we can add diodes to prevent the low voltages and take only the high voltages. And the point is that we can do whatever we want with it once it reaches our plug. And it's as simple as that. And I don't know if it was this class, but there was someone who was interested in making an electromagnetic generator. That's all you need to do. You put a magnet in a coil and you start spinning the magnet, and you've got yourself a generator. It's as simple as that. Any questions on this? So obviously the complication of this is now the math and which kind of derivatives I'm going to ask you guys to do. It's going to be you. I would just recommend that you practice the problem. Okay. Though there is a quiz next week for you guys on a Wednesday. It's not on what we did today. It's everything on magnetism up until our last class, all right? Not including induction. Induction and LR and LC circuits are going to come on the next quiz. Okay. Though I really do ask you guys to review your derivatives if you can, because they're going to be. I mean, I can't avoid them. They're going to have to be a part of it. Okay. Okay. Let me stop this.